Maybe
So yeah, good afternoon and welcome to the communication signal processing seminar. Before I introduce the speaker for today, I just want to thank a few people. One is Shelly Feldkamp, who's running the thing behind it. Otherwise, the thing doesn't work. And then the KLA, our sponsor, and as well as the two research groups, NCIS and Signal Processing and Machine Learning. So our speaker today is Mert Gürbüzbalaban, who's in, I hope I pronounced it fine. Or yes. I may not have gotten the accents right. I don't know all the Turkish accents, but that's fine. He's an assistant professor at Rutgers University. Before that, he was a postdoctoral associate at Leeds at MIT. He's broadly interested in optimization and computational science driven by applications in large-scale information and decision systems. He received his bachelor's and BSc in electrical engineering and mathematics as a valedictorian from Bogazici University, Istanbul, Turkey. The diplôme d'ingénieur degree from École Polytechnique in France, and the MS and PhD degrees in applied mathematics from the Courant Institute of Mathematical Sciences, New York University. So he received the Kurt Friedrichs Prize given by the Courant Institute of New York University for an outstanding thesis in 2013, bronze medal in the École Polytechnique Scientific Project Competition in 2006, the Nadir Orhan Bengisu Award given by the Electrical Electronics Engineering Department of Bogazici University to the best graduating undergraduate student in 2005, and the Bülent Kerim Altay Award from the Electrical Electronics Engineering Department of METU in 2001. He received funding from various sources, including multiple programs at the US NSF. He's going to talk about stochastic gradient descent, neural networks, and heavy tail phenomenon.
Okay.
So go ahead, Mert. The floor is all yours. If there are any questions, I'll look at the chat, but people may interrupt and ask it as well.
Okay, thank you very much, Vijay and Nejmiye, for the introduction, for the generous introduction and the invitation, and thanks to Shelly as well for everything, for all the hard work. And it's really a pleasure to be here and talk to you about my research. So today I'll be talking about stochastic gradient descent methods. These are, I would say, the default methods used in data science in many machine learning applications. And I will tell you about the story, how we got more insights about them, and what can we do about them, and how we can improve them, and so on. So we will try to understand stochastic gradient descent methods better in the context of machine learning today. Okay, so let me start with the traditional optimization setting in machine learning. So the problem is that we have data, and we are trying to learn a model that is predictive, right? So if you want to fit a model to data, what do? You go and minimize the loss function, right? That measures how you fit the data. But if the data is random, naturally, you will try to get the best average performance due to the randomness. So the classic formulation that you need to look at is that you are trying to minimize the expectation of a random function, and the randomness is caused by the data. So you have some input-output pairs. You want to have a predictive model. You have parameters, and you will choose these parameters for the best prediction according to the loss that you will define. So this generic setting is known as risk minimization in statistics in machine learning, and it is like a framework that covers a lot of interesting problems. So in the simplest setting, like if you have data points, a natural thing you want to do is to try to fit a model to data, right? So the simplest model would be a linear model. So if you go and do linear regression, essentially you are trying to fit a linear model to data, right? So in this setting, your linear, the parameters will be like your regression coefficients, right? That you are trying to learn. And if you choose your loss function to be quadratic, you will be in the least square setting, and you will be doing some sort of standard linear regression, right? If you add some sort of sparsity inducing penalty, like L1 norm or some other type of norm, you will be still in the setting. You just need to change your loss function accordingly, right? Another setting that is, that you can think of is the classification. So we have data points. Maybe here you have blue and red data points. You are trying to figure out a boundary that separates them, right? So you are trying to essentially find the parameters of this line or this like hyperplane that separates your data. So if you choose your function, for instance, as the logistic loss, then you will end up getting the logistic regression problem. If you choose it as the hinge loss, you will get the support vector type of formulation. But essentially, many classification or regression type of problems would fall into this framework. Another application that is also quite relevant in practice is deep learning. So in deep learning, the function, the loss function that you have, like your predictor, has a nonlinear structure inspired by how the brain works. Essentially, this is like a neural network used in deep learning, where you have some input signals and you have some output. So essentially, what a deep network does is that it transforms your input through some layers, and each time it applies a nonlinear transformation. So you have these links. So these links tell you how you should amplify your signal from the previous layer to the next layer. You do some sort of offsetting and then some sort of thresholding. And the idea is to try to fit to the input-output relationship that you don't know about by adjusting the knobs of your network. So the standard sort of application of this is that suppose you have images. So this could be used in image processing, for instance. You have lots of images. You want to recognize them, right? So what you do, you vectorize your image. This is your input to the network. And each time I show input 1 to the network, you want the output to be 1. So if you show a digit 2 to the network, you want the output to be 2, right? So essentially, you want to adjust the weights of this network so that you will sort of approximate the nonlinear transformation, whatever it is, between the digits, the pixels, and the digit values. Okay, so in this setting, the model parameters that you want to learn are just the weights and the bias and the thresholding and so on of your network. Okay, but in practice, I don't know the data distribution, right? Think about you have some images that are handwritten digits. I have no idea what is the distribution of the pixel number 3, right? I just have lots of images, but I may not know what is the distribution of the sort of pixel values, right? So essentially, the idea is that, yes, if I would know the underlying data distribution, I could compute this expectation, but I don't know it. So I have to go and check my data so that I kind of approximate this expectation with a finite average. The idea being that you have n data points, and what can you do? Because you just approximate the expectation with a finite average. The thing is that in modern applications, you have huge number of data points, and you may have huge number of parameters. So for instance, in some modern networks, you may have millions or even billions of parameters, and you may have a lot of data points, right? Think about all the images on the internet regarding handwritten digits, right? So there may be so many of them. So how do we solve these problems? The first, so that's one question we should ask ourselves. Another thing we should understand is that when you go and sort of try to solve this average, so when I'm doing this this is called empirical risk minimization, I'm having a finite average to approximate the expectation. This problem, based on data, is just a proxy to the original problem. So in other words, even if you go and fully optimize this finite average, the solution will not coincide with the original problem you have because you have randomness and you have noise in your data, right? As a consequence, often we just want to solve these problems up to a certain accuracy. And in the context of deep learning, these problems are highly non-convex, so we don't have hopes of finding the global minimum, okay? So we will be fine if we kind of find a local minimum for computational purposes. So the question is, how do we kind of, what is the simplest thing you can do if you want to solve these problems? So the thing is that the gradient descent, if you think of gradient descent, it's the simplest method you can think of, which will scale well to high dimensions. Something like Newton's method would have trouble in high dimensions in terms of storage and per iteration cost. But the gradient descent will have problems too, because if I want to compute the gradient of my objective, I need to go through all these data points one by one, right? If I have 10 million data points, I have to visit all of them to find the gradient. So this is really impractical or infeasible, actually. So what people do in practice is they replace the gradient with a cheaper estimate. So that is the basis of the stochastic gradient descent method that I will talk about. But just to mention a few applications to motivate the discussion. So deep learning can be used in many contexts. So why are we interested in deep learning? That's a question you may ask. The standard application would be computer vision. So these days people are excited about self-driving cars, and essentially when you're driving, you need to recognize cars, passengers, and so on. And deep learning can be used here to identify sort of objects. And I know that in Michigan, I think you guys have some nice test platform to there's like a self-driving, I think, vehicle, like a shuttle bus in Michigan. So basically, this can be used in that setting. Otherwise, machine translation, like if you want to translate languages, deep learning has been quite successful. Or otherwise complicated predicting tasks, right? So suppose that you want to predict some pattern in social media. Maybe you want to predict Twitter trends or some kind of success of a movie, right? Any kind of tasks, if you have good features and if you have a nonlinear map, you could use deep learning to train a classifier. Right? And more recently, I've been checking about COVID-19 papers, and people also have come up with some state-of-the-art classifiers that can diagnose a patient. Suppose you have a lot of, let's say, symptoms like maybe fever, I don't know, temperature, fever like blood pressure, and so on. Like how do you classify whether someone has a sort of COVID or not, right? So this is a classification question. And in many applications where you need this kind of predictive modeling, deep learning has been like a powerful tool. Again, if I just go back to the algorithmic side, how do I solve these large scale problems? Well, due to computational reasons, right? What you do is you go and work with subsampled data. So if you have 10 million data points, you just go and maybe sample 10 of them randomly, or some smaller subset of them randomly. And from the smaller subsample, right, you estimate your gradient. So now this will be much cheaper, because if I want to update my vector, xk is like my current estimate of the model, right? I am updating it. So if I can form this stochastic estimate of the gradient quickly, then I will have this quick progress. The disadvantage is that you will have errors, right? So this stochastic gradient estimate you have will be accurate only on average. So because you are doing some randomized sampling of the data, maybe in expectation you have the right gradient, but because of the stochasticity in the choice of the data, you will end up having sort of a noise in your iterations. Okay, so there are different ways of sampling data, and I had a lot of work in different sampling mechanisms and so on. But here, for simplicity, we will take that you just sample every data point with equal probability, at random. So this is the setting that we are interested in. Okay. So just to give you the basic intuition, and also, I mean, I should say that stochastic gradient is used heavily in the data science industry. So if you look at companies like Google, Facebook, Netflix, Amazon, typically a lot of their operations, I mean, in a lot of applications, they will be using SGD. So it's like a very popular method that works quite well for many problems. Of course, we have, for customized problems, we have a lot of specific methods. I will tell you more about it, but SGD is like a very kind of successful method in practice, I can say. Okay, so let me just give you a little bit intuition about how this thing works. So gradient descent is a little bit like the picture on the left. So you are sitting on the top of a mountain. When you follow the gradient direction, essentially you are flowing with gravity, and you are trying to figure out some sort of low energy kind of place where eventually you will converge to a local minima. So obviously that local minima that you converge will depend on where you start, right? If you start from the right, maybe you will converge here. If you start from the left, maybe you will converge here. Okay. So how about stochastic gradient? Well, stochastic gradient has noise in it, right? So because of this noise, you will not be following this curve, but you will be kind of zigzagging and jumping around it. So you can think it as a ping pong ball, basically. So from place to place, you jump. And as a consequence, I mean, there's no reason why you should converge to the same local minima, right? So for instance, here, it's quite possible that the stochastic gradient step here, maybe you will end up converging to somewhere else. So in practice, actually, when you launch these algorithms, often they converge to different places. So they find different solutions. So the question you may ask is that, which local minimum is better for me? Because remember that at the end of the game, even if I'm optimizing and finding a model, I want performance on the unseen data, right? So this is known as generalization. So you are trying to achieve the best performance in unseen data. So the question you may ask is that, which kind of local minimum I should be searching for? Okay. So this is actually an old question. So people thought about this, like what kind of local minima we should find in non-convex settings. And there is a kind of a very nice paper going back to the 90s by Hochreiter and Schmidt-Weaver that argues that, think about the picture here. I have two local minima, okay? So one of them is very sharp. You know, it is really a kind of a very deep and sharp valley, whereas the other one is sitting on a wide sort of valley. It's like a sort of you can think that this is like a flat valley. So the argument they make is that, based on some Bayesian sort of approach, they argue that you should be converging to the one on the right, because the idea is that the one on the left is doing some kind of overfitting. So maybe you don't have enough data, so you see these zigzags in your sort of in your surface. So this approach tells you that, okay, it's better to converge to the one on the right, okay, because it's lying in a wide valley, and essentially you could under certain assumptions you could argue that this is a better thing to converge to. So now here's the interesting part. So you launch gradient descent and stochastic gradient descent, and then you look at what they do. So interestingly, gradient descent typically overfits. So meaning that gradient descent goes and finds this minima here that is on a sharp valley. Whereas stochastic gradient descent typically prefers wide minima. Okay, so in other words, gradient descent is not something that is good to do just from a computational point of view. It's too expensive. But even if you do that, actually you overfit. So somehow stochastic gradient descent, because of its dynamics, has this ability to filter out bad local minima. I'm saying bad in some parentheses, and then figure out this like wide minima. Okay, so the question you may ask is, why does this happen? Because if we understand this, then we may be able to alter the dynamics of SGD, or we can have better algorithms. So what makes SGD work so well? That's the question that we want to ask. More specifically, we want to ask, why does SGD prefer wide minima? So that's the question. Obviously, this question has to do with the noise, right? The only difference between gradient descent and stochastic gradient is that you have more noise in stochastic gradient. So somehow something about the noise structure should be leading to convergence to this wide minima. Okay, so this is the question that we want to understand. And this is joint work with Levent, Sagun, and Umut Şimşekli. And with this work, actually, this was published last year in ICML. This was the start of the things for me in terms of how the noise works in SGD. Okay, and after this sort of initial results, that I will motivate experimentally why, how the noise behaves, and then I will provide you some theoretical sort of background, theoretical analysis that can explain, some of the interesting behavior of SGD, and then we will discuss how we can get better algorithms. Okay, so let's try to understand the noise. Okay, what is the noise? Well, I have a lot of data points, right? So by the way, I mean, I may not be able to see the chat button sometimes. So, if you have questions, please feel to interrupt me. I may not see if you are writing, or I may not be able to see exactly your comments. So feel free to interrupt me anytime. So let's try to understand this noise structure. So what is the noise? So, well, you go and sample data, right? So each data point you are sampling, you are taking the gradient of that data point, gradient of the objective with respect to that data point, and then doing some kind of average, right? Because I am doing sort of IID sampling, essentially your gradient error will look like average of IID random variables, right? This is like a mean estimator. If you go and check, I don't know, n data points, the mean of the data points will look like, just like the variance of this estimator will decrease, right? And the more data points you have, maybe you will have a better estimator. So the general thing you can so in the literature, people usually make some assumptions to make the analysis easier, right? So a common assumption that people make is that, imagine that the variance of my iterations, right? I am iterating, and imagine that the variance of my noise stays bounded. So I work myself in stochastic approximation theory and in stochastic optimization. This is a very common assumption. So you assume that noise has, finite variance. So under this setting, right, everything has finite variance. So you have the central limit theorem type of approaches that tells you that the average of random variables should behave like a Gaussian, right? And then essentially, if you have enough bed size, you could show that this thing will behave like, your noise will behave like Gaussian. And then you could just, if we want to understand how the noise structure works, if you want to model the noise, you could just say that, well, what SGD is doing is like, maybe you have some sort of drift that is pulling you towards the minimum, but you have some sort of noise, and let me model this noise with a Gaussian distribution. ZK is a Gaussian. Okay, I have some step size eta, and then maybe something that depends, sigma square is like how much variability I have in my function. So this is like a model of SGD that you can try to understand. But the thing is that discrete structures are usually harder to analyze. Right? So if you think about combinatorial optimization versus convex optimization, right? So continuous time models can sometimes be easier to work with to get some explicit results. So people have been interested in, and in practice, often you may let the step size go to 0, or you may use a very small step size so that the algorithm iterates converge. So people then thought about, okay, let's sort of approximate this discrete time sort of dynamics. If the step size is small, I will have some kind of continuous time limit. So what happens is that if you, in gradient descent, the limit is the gradient flow. So it is like an ODE that you have, okay? But when you have noise, actually you have like what we call a stochastic differential equation, right? So you have a differential equation, but it has some noise in it. Because of the noise part, you will be converging to a Brownian motion-driven SDE. So in other words, you can think it as like, this is gradient descent, but you have some sort of white noise on top of it. So in stochastic control, for instance, you would have this kind of evolutions. You may have seen some in some other context. So then the nice thing is that because we have a continuous time model, we have a lot of intuition about what's going on here, because this process is known to admit a stationary distribution. So essentially, this is a process where your distribution evolves, and it turns out that even if f is non-convex, this process will have a stationary distribution. So people have, for instance, people who worked on simulated annealing type of algorithms in the past have worked on processes like this. This is well studied in the literature. And then based on this SDE, you can try to draw some conclusions. So maybe the equilibrium distribution of SDE is this way. That's why I will be kind of having this kind of behavior. These are just sort of models to understand SGD. So there was an interesting paper that we have seen that looks at sort of these processes, and then sort of argues that what SGD will be spending more time in places that have a certain width, and this width will be determined by some ratio called the step size divided by the bed size. So this ratio arises in a number of papers in deep learning. So because the step size controls your noise, and remember, bed size is how many sample points you had. So the ratio of these things can control your noise level. So when you look at these papers, you can draw some conclusions, and then you could also argue about how you should choose the parameters. If you want to sort of converge to certain. So essentially, it gives you some intuition about how you should choose your parameters. Right? Okay, this was nice, but until we did the following experiment. So we just took a network and look at the distribution of the noise for the gradients. Because in the network, I could compute my gradient, I could compute my stochastic estimate of it, right? This way I could generate a histogram, right? So here, for instance, in orange, you see if the noise would be really Gaussian, if you look at the error that you have, the norm of the error should look like this orange curve. Because Gaussians decay exponentially, right? So the decay in your error should be exponentially fast, right? So that is what these models are saying. But if you look at reality, this was on a realistic network. Actually, if you look at the norm of the errors, you see that they are decaying not as fast. They are decaying a bit slower. And in particular, you can have large values. So from this experiment, you see that maybe Gaussian modeling is not the right thing to do, because at least experimentally here, you see that things don't really look Gaussian, okay? So basically, these models don't match with the practice, what's going on. And on top of it, there are some problems with the theoretical statements. So first of all, when you are saying that when you say that I'm going to be looking at the stationary distribution and try to get some intuition about it, right? There's a nice paper by Bruce Hayek from 80s that shows that this would require exponential time. So for reaching, this kind of stationary behavior that these papers talk about, right? You need e to the d iterations, and d can be millions. So clearly, somehow SGD is more efficient. So somehow, if you want to think about this non-convex surface here, if you would want to exit from one local barrier, you would need exponential time. But SGD is somehow very efficient to find the right local minimum, right? So this doesn't match too much. I mean, this doesn't really match the practice. Okay, so then we thought about it. So essentially, in many applications, you may have what you call heavy tails. So if the tails decay slower than an exponential, we call it heavy tail distribution. So for instance, if you have a polynomial decay, then you will have a heavy tail distribution. So it looked like kind of the error, the gradient errors, the noise has this heavy tails in it. So then if you think about it, why that they may be the case, the reason is the following. If your variance during the iterations are not bounded, uniformly bounded, then the central limit theorem does not hold. So it turns out that if your variance is growing over time, there is a generalized central limit theorem that tells you that actually the average should be heavy-tailed. And so in the usual case, you get a Gaussian distribution, right? So if your variance is not bounded, it turns out that you get another distribution called alpha stable, symmetric alpha stable distribution. So this is like a picture of this distribution. So these distributions are like, if you wish, the limit of averages if you don't have bounded variance. So in other words, they decay a bit slower. So for instance, when alpha is 1.5, right, they decay slow, but when alpha is 2, they will be like the Gaussian. So in other words, somehow we thought that, empirically speaking, these generalized models that can help us understand SGD will fit better to what's going on with the practice. So then we propose to model SGD with this type of heavy-tailed kind of distributions. So we model the SGD noise with heavy-tailed distributions and try to infer, what can you get out of it, right? So you can do some kind of continuous time approximations, and I show that actually the dynamics you get is not going to be Brownian motion driven, but it will be something else called a Levy process. So Levy processes have jumps in them. So for instance, here you can see that the Brownian motion that you may have seen in different contexts, typically it has this yellow paths. It's continuous, right? But if you have these heavy tails, actually you may have jumps basically. And you see here, you see an example. Okay. So we propose to analyze SGD with this model, and then we could add up a lot of results from the statistical physics literature to the deep learning setup. So one of the results that you can show is that if you consider the exit time from like a local energy barrier, when you are searching for a local minimum, you could show that because of the heavy tails, this exit time is not exponential anymore. It doesn't depend on the height, but it depends on the width of your local minima. So for instance, in this case, the minima on the left has a small width. Therefore, these processes will be able to jump out of this local minima in a fast fashion. Fast meaning that it will be polynomial in the width. And we can have an exact characterization. In the papers, we also developed exact characterizations of these things, like how much time you need to take and so on. Okay. And then when you go and try to fit an alpha stable distribution to your gradients, essentially experimentally, these distributions leads to better fit in terms of what's going on in practice. Okay. So what's really happening is this. So this is the classic simulated annealing setup that I can show you. So in non-convex optimization, if you use simulated annealing type of algorithms, it may take you exponential time, but eventually you localize on the global minimum. So your stationary distribution is a Dirac on the global minima. So you wait enough, and then somehow you localize there, right? So this is the standard setting in SGD if you have Brownian type of annealing noise in it, right? So this is what is happening, what standard models say. Okay, so then you can ask me what happens in a Levy kind of process, right? In the equilibrium. So it turns out that your stationary distribution has support over all the local minima. So you are not guaranteed to converge to a local minima. You could converge to any of them, okay? But the question is about the probability, the mass you have on these local minima. It turns out that in the equilibrium, you will have much more mass in the wide minima. These probabilities, how much time you spend on the local minima with wide width, will be much larger, right? So essentially, this is the interesting thing. So this essentially this explains what you see in practice to a certain extent. So these models tell you, okay, you will converge to some limiting regime with SGD. Think about this ping-ponging that's going on. So you, in polynomial time, you will converge to some distribution. This distribution will not be globally optimal, obviously, because you would contradict the NP hardness results. But actually, because you are spending much more time on wide valleys, and these wide valleys generalize well, that we think is one of the foundational reasons why SGD is working well. So this theory was sort of that we developed was sort of trying to explain why SGD works well, and this approach, as you can see, can explain why SGD converges to this wide minima. Okay, but it doesn't tell you where the heavy tail comes from. We just say that assume that it's heavy tail, then we have a really nice theory that we can back up with experiments. So here on different networks, we kind of look at experiments. Again, these are standard computer vision tasks. So MNIST is a data set for handwritten digits. We are trying to recognize them. So CFAR 10, CFAR 100, these are like basically you have different classes of images, like you have cars, automobiles, and different classes, and you're trying to recognize these objects in the images. So these are benchmark data sets. So in the paper, we look at different architectures and different network styles and so on. But let me tell you some, some subset of these results. So the first thing we looked at was, we said, like, let's play with the network. So here we are taking a fully connected network. Everything is connected to everything. So we play, let's say we take the depth constant and play with the width, meaning that how many neurons you have on each layer. Then we take the neurons constant and play with the depth. Okay, so this is like, we make the network larger, either play with the neurons on a layer or. So when we do that, actually you see that when we estimate this tail index, remember this parameter that tells you how fast you decay in terms of your distribution. 2 means Gaussian, anything below 2 means that you are heavy tailed. Okay, so here basically you see that all these numbers are kind of away from 2. So this is an indication of non-Gaussianity. And when I make my network larger, also you see that my tail index drops a little bit. And it depends on a little bit like the data set, but essentially bigger network somehow is leading to heavier tails in this. So the dimension increases, somehow you have heavier tails, okay? This is like an experimental thing. And we also look at the effect of the bed size. So we play with the bed size, and often what you see is that if you change the bed size, if you increase it or decrease it, what we have seen is that here obviously if you sample the whole data set, then you don't have any noise. But in the small bed size regime, we have seen that things stayed heavy tail. Okay, so in the paper, we have a bunch of other theoretical results. So for instance, classically people work on the, let's say, local convergence of SGD. So we have some, complexity results and so on, assuming heavy tail noise. The traditional setting would be, okay, if you have bounded variance, then I need 1/t iterations to converge to a local minimum, etc., etc. So in the paper, we have done more theory about this. But maybe you could check out the paper for more theory, and we have a journal version of the conference paper. But let me tell you some other interesting connections. So about the same time of our work, actually, people look at the deep learning set from a different perspective. So there are really nice papers from Martin and Mahoney. They look at the network weights. So I'm looking at the iterations, right? So I'm looking at the gradients basically. They are looking at the iterates, but obviously they are related, right? So if your weights have heavy tails, then your gradients will inherit that heavy tail most likely. So what they have seen in these papers empirically is the following. So somehow when you start training, everything looks Gaussian, and you don't see much this heavy tail behavior. Because think about it, the first iteration, right? You are at a point, you will jump to somewhere else. I mean, it's not that you can have some crazy jump. Let's say somehow people have seen that this heavy tail phenomenon kicks in, not in the beginning. Sometimes, somehow like things evolve over time, and after a certain level, you have this heavy tail phenomenon. So what they have observed was this heavy tailedness in the network weights from an empirical perspective, which is in line with our results. Okay, so somehow when you increase, two things are very common. Somehow if you increase bed size, you are doing gradient descent like thing, and then that doesn't work well. Okay, and the second thing people see is that somehow this heavy tailedness kicks over time, not in the beginning. Okay. So these are all empirical. This is like a lot of empirical field, and as a theory person, we are trying to understand this this a bit better. But after our paper, the good news is that people have seen this heavy tail behavior in different contexts. Like for instance, when you are trying GANs, when you're trying when you work on attention models and so on. There are a lot of different papers that have observed a similar phenomenon. So basically this heavy tailedness thing that we observe seems like well justified in many settings. But to us, it was a bit mysterious. So the first thing, I mean, so basically we have a great theory that is nice and it explains what's going on and so on, but what are the origins of heavy tails in deep learning? Like, where do they come from? And why do they arise gradually over time? Like, okay, the second thing you can ask is that typically heavy tails are associated with better generalization from an empirical perspective. So if you have heavier tails, people have seen that, oh, you have better generalization. And somehow, if you make your bed size small, you have heavier tails. I mean, intuitively speaking, small bed size means that you have more noise. So you may expect this, but somehow there's like a non-trivial relationship between the bed size you have and the tails you have in your noise. Okay, so this connection is not well understood, and we want to understand it better. Secondly, you can ask, this heavy tailedness, is it something that is only specific to deep learning, right? You can give a gazillion of applications like linear regression, lasso regression, logistic regression, support vector machines. So does it happen in those settings, right? So that's another question you can ask. Now that we discovered this in the heavy tail setting, we could ask, how about these other settings? So we in a recent paper, actually, we showed theoretically why these we can prove that theoretically these heavy tails could arise if the step size is chosen appropriately. Okay, so in other words, we have a theory that can explain this in linear regression, and as most of the engineers, what we do is that we go and show that this theory for linear regression can help you understand deep learning as well. So we develop a theory in a specific setting, but it has ramifications for the general deep learning setting. Okay, so what is linear regression? Essentially, it's like quadratic optimization, essentially, right? So you have input V, you are trying to fit to output Y. So traditionally in statistics, people use beta, but here beta is reserved for us for some other things. So here we are using X is the parameter that you want to learn, right? So what kind of recursion you get in SGD in this linear regression setting? So, when your function is quadratic, the gradient is linear, right? So you should get something like an affine recursion in gradient descent. So when you do gradient descent on a quadratic, you should be getting an affine recursion. Okay, but here, because we are doing stochastic gradients, what you end up getting is that you have a linear-like recursion, but it is a random recursion. So your state xk minus 1 is multiplied with some matrix plus something. So it is affine, but this matrix M and Q, they are random. Okay, so you can think this is called like a stochastic affine recursion. It looks like affine, but it's stochastic. Okay, and as you can see, my noise has a multiplicative component. So for I'm talking to the optimization folks here. So typically you can have additive noise and multiplicative noise, right? Here you see that my random noise has a multiplicative behavior, and it has an additive behavior. So it is both, right? Also in control, right? So you can have noise that affects your state. You can have evolution ABCD, and noise can be multiplicative to the state, right? The same thing here. You can think it as a multiplicative sort of noise effect. So just for the sake of the talk, I will specify to a specific setting. Imagine the most simplest setting. You know, the data is Gaussian, sigma square times identity. You know, everything is nice and Gaussian. Maybe maybe y, which output variable that you want to predict, is maybe having some kind of nice coming from some nice continuous distribution and so on, right? I'm in the linear regression setting, but I'm assuming that the data is very nice, just for the simplicity. Okay, what we are after is that we are trying to characterize the tails, right? So I have stochastic gradient recursion. This will converge to something, but what is that something? How fast it decays, right? Because if my iterates are sort of have this heavy tail, then the gradient will pick that up, and it will explain what I was showing to you in the experiments to a certain extent, right? So that's what we are trying to do. So in other words, we are trying to estimate this alpha. So the stationary distribution you have, the solution that you find with SGD, has some distribution. The question is that how fast it decays. So this is known as the tail index, right? If the tail index is 3, this is like the blue curve. So you have fast decay of the solution. It means that you are localized in space for signal processing folks. Basically, bigger tail index means that you are localized in space, right? So whereas if tail index is large, it means that you are a bit jumpy and you are not localized in space. Okay. So this is our main result. I think I don't know how much time I have, but maybe like 5 minutes or 10 minutes.
Yeah, you've got 5-10 minutes. Yeah, 10
okay,
minutes.
Thank you, Vijay. So let me kind of explain you the main results. So the main result tells you that you will have a heavy-tailed stationary distribution. Okay. And I can tell you exactly what is the tail index. So the tail index alpha will be solution to some nonlinear equation. Remember, M is like my iteration matrix, and essentially, if you solve for alpha, again, M is something I can write down because it's my iteration matrix. So if you solve for this equation, you get your index. Okay. So how do we do these things? Essentially, we were inspired by queuing theory results. So I'm not a queuing theory person, but I saw papers, and my collaborator Lin Zhu, who showed me some papers from Goldie and Kesten from 70s. And in queuing theory, you are interested in like when customers arrive, what will you able to be serve them on time, and whether you will have this kind of heavy tails. And using some of their results and kind of more modern results from recently, we could characterize that this kind of heavy tails arise in linear regression. So what does it say? Even in linear regression, you have heavy tails. So, and even though we do this theory for linear regression, we could do it things for logistic regression and other things in a slightly more generalized context. We cannot do fully in deep learning, but even things, it means that SGD has these tails even in sort of in a simple problem. And what we can show is that this tail index is monotonic in the bed size and step size. So it means that large step size will incur heavier tail, and small bed size will incur heavy tail behavior. And that then, because heavy tails are associated with generalization, this sort of explains why you should be working with smaller bed sizes. And here's another result that I can tell you. So there's a critical step size. Okay, if the step size is small, you have all these moments and so on. Everything is nice. So if you increase your step size, your tail index will drop monotonically. So essentially, things are nice if you have small step size. There's the critical threshold. If you pass it, things become heavy tail. Actually, a similar result was obtained by Srikant and Lei Ying actually last year. So where they show that they're interested in TD learning, and they can show that there are some examples where the similar kind of threshold can happen, below which you have light tails, above which you have heavy tails. Here, because we have a more sort of like a specific model with Gaussian data, we could kind of compute all these like thresholds in a more explicit form, and we can show monotonicity, meaning that like the tails will get heavier and heavier if you work with larger step sizes. And because heavy tails allows to explore better, you will be ending up generalizing better and finding this local minima, finding this local minima that lies in these wider surfaces. And people actually, this also explains some of the experimental results. People have worked with, have seen that large step sizes helps in deep learning. And this theory sort of explains that actually what's happening is that you're kicking some heavy tail behavior, and that's why things are happening. So I'm not going to be able to talk too much, but in the paper, so we can characterize like how your moments grow. Essentially, it turns out that, remember I was saying that somehow over time this variance blows up in deep learning. So we could quantify how fast things blow up, which moment stays finite, and so on for this particular model we have. And we have some sort of also central limit theorem that tells you that if you average iterates, you will exactly get an alpha stable distribution. Remember that this alpha stable distribution I talked about before was a bit like experimental. What we can show it in the deep learning setting. And just let me quickly finish like a few experimental results. And so we can, these experimental results I mentioned, we can see them in fake, I will say synthetic data, not fake, but synthetic data. So the results check out. But in deep learning as well, when we look at what things happen, how things happen, so the ratio eta over b that I talked about, right? So in linear regression, we can show that it's monotonically decreasing. And in experiments, actually, we have seen the same behavior in deep learning. Okay, so in some sense, the theory that this is the theory we developed for linear regression that tells you that you will have this kind of behavior that's monotonically decreasing. And in deep learning, so there are some papers that argue that you can think deep learning as some sort of kernel regression or some sort of least square regression. So that may be the reason. So somehow we see that experimentally similar results are, these results are sort of, you know, meaningful in the deep learning setting as well. So if I just wanna, I won't have time for it, but basically right now that we understand that SGD has heavy tails, by invoking some kind of artificial heavy tails ourselves, we could also improve SGD training. So essentially, we are arguing that SGD works because it has heavy tails. But if you know that, why don't you incur some heavy tails yourself to the training process, right? So we have, I'm not going to be able to talk about it today, but inspired by these results, we were able to sort of come up with an initialization scheme in deep learning that invokes heavy tail behavior right from the beginning, so that you don't have to wait for this nice sort of heavy tail regime to kick in. Anyways, you could check out that paper online. If I want to summarize, basically stochastic gradient descent is like the most common algorithm that you can think of, but still we don't understand so many things about it in non-convex settings. And one particular behavior we see is that this heavy tails in the gradient noise helps you to generalize better, allowing you to jump between these local values in a faster fashion. And we have a theory that sort of, you know, explains partially why this is happening. And we think that we will be using this theory to get better and faster algorithms. I think with that, I will stop and thank you for listening. I may be over time like a few minutes. Oh, by the way, I just saw that there are some chats.
Yeah, there are a few talks, chats there. So, okay, maybe one was, I think Lei was asking, larger batch size would lead to a lighter tail.
Yes, that is right. Maybe did I say it the other way around?
No, I think in the theory you said that just from one of your simulation figures, this seems go the opposite way. So I was just curious.
Oh, okay, like the other one, like here.
The one, yeah, the one before that, the one before that. Yeah, the next one.
Okay.
Yeah.
So let me see. So here we increase the batch size. Let me see. I can't see my screen. Just a second. So
the batch size, so the alpha should be increasing, right? When you have a larger batch size.
Let me see. Yes. So alpha should be increasing, but first of all, the result that we had was for linear regression, right? So that's one thing. It's a good question though. Another thing is that estimating these indices, you know, there may be some actually, you know, some maybe it may be up to some error bar.
Right.
That may be the reason. But the thing is that clearly the index is very far away from 2.
Yeah, that's
I
true.
think that's the message. But it's a great question. And some of the results I presented is also related to your paper with Srikant from last year. Yeah.
Okay. Yeah, right. I have a few comments on that after the question. Yeah.
Yeah. So let me finish this question, then Lei can take over. He's one discussant, and I'm the next discussant. So I'll take over after that. So, so the question was that Kleinberg et al., and I don't know who the references are, showed that SGD can escape sharp local minima with constant step size, since the noise has a smoothing effect on the landscape. The landscape is convolved with random noise. I guess that's the logic there. Is there any connection between your work and theirs?
So when they talk about escaping sharp local minima, they are not talking about, I think, escaping a whole like a barrier. So they are thinking of a local result. So there are these local results about SGD that tells you that locally you get rid of like some epsilon ball, right? But it doesn't mean that you will be jumping over to the next basin of attraction. So I should check out this paper more carefully, but to my knowledge, the Kleinberg paper, maybe there's another one that's recent that I haven't seen, but they're talking about more like a local, so around the local minimum, what's happening, right? So, but not about jumping to another. I'm happy to, yeah, I think the talk is being recorded, so definitely I can provide the
yeah, if you can send me the slides, that's fine. Yeah,
right. But this is a good question. So there are different lot of algorithms about escaping sort of local minima, and here we are more on the global sort of landscape here.
So let me go with Lei first. So we'll have to stop sharing, and then Lei can share after that. Okay. So you'll be the first discussant. Yeah.
Right.
Okay.
Right. So
sharing.
Yeah, I like this discussion thing because it's you know, more alike and right.
Yeah. Can you see my screen?
Yes.
Okay. So our first, very nice talk, Mert. I really enjoyed that. So I just want to briefly mention there's the related work Srikant I did, which is for linear stochastic approximation applied for reinforcement learning. So I think the stochastic linear approximation is kind of similar to what you have introduced. We look at the theta as a parameter of, for example, in the TD case. Then we have this multiplicative noise and also additive noise. And we also find this interesting heavy tail phenomena. What we showed is given learning rate epsilon, if we look at the higher moments, if the 2m moments such that m is smaller than 1 over epsilon, then the 2m moments behave like the moments from a Gaussian distribution.
Right.
But when it's higher than that, then at a steady state, the moments become infinity. So that means for a fixed learning rate, then at the steady state, all the distribution are heavy-tailed in that sense, right? If we look at basically the moment generating function does not exist. So the similarity, I think, with what you just presented is, first of all, we both observe heavy-tailed phenomena, and it's come from multiplicative noise, we believe. And the second is the learning rate become a deterministic factor for the tail distribution. The difference is I really like your talk because you provide a very comprehensive analysis about the dependence of these tail index, really how they're related to the Hessian, related to the batch size, and related to the learning rate. And you have the closed form expression to calculate the alpha as well. That's really, really nice. And also you provide insights of how that heavy tail distribution help generalization and in deep learning. So I have to say at least before that, we view this heavy tail distribution as a negative thing, right? For the linear stochastic approximation, you have a unique equilibrium point. So you want to have as much concentration as you can, right? But try to avoid heavy tail distribution. But here, what you're saying is for non-convex optimization problem, like a deep neural network, actually it helps because you want to get this local minima, which has width instead of depth. So that's really exciting. And I definitely would look forward to look into that. For example, to see like in the reinforcement learning case, can we say anything about that? Like heavy-tailed actually helps the learning in reinforcement learning as well. That'll be very interesting.
Right. So I think, so in your paper, so it's a nice paper. So in the TD lambda setting, right, if you have a non-convex problem, actually it will help you.
Yeah, so we want to, so in what sense, like what kind of theoretical result we can say, right? Because we look at the linear case where they only have a unique equilibrium point. So certainly if the TD lambda, if we use neural network, it becomes non-convex, right? So it'd be interesting to see theoretically what we can say in that context. So that's really exciting for me. Another difference I noticed is that in our case, we consider Markovian noise. So the X we consider is a Markovian system. In your case, it's IID. That's some minor difference from technical side. Yeah, so the question I have is, if we look at the Markovian noise, I think the mixing time of the Markovian noise will also have an impact on the tail distribution. So any comments about how the mixing time will play a role in the tail index?
Right. So I think, so here we are showing exponential geometric ergodicity, right? So you have in the right metric, you have some exponential contraction. My guess is that at least in this setting of linear recursions, your rate will be the worst of your mixing sort of behavior versus this rate.
Right.
So I think you will pick it up. So one can also look at what we can also do is that the noise does not have to be IID. So if it is like a martingale difference noise, it is still going to work, but it is really complicated. So that is another setting. And I think like, I also, liked your paper. And so here we couldn't use directly your paper because I think in the paper, this was like a more on the Bernoulli case. So we couldn't use some of your results directly, but I think maybe your paper is the first one that talks about heavy tails in the reinforcement learning setup, and definitely kind of very related and interesting. So.
Right. So for our paper, what we did for the negative impossibility result part is we just provide an example. It's not as comprehensive as you did. Yeah. And for the higher moment for the bound, like the Gaussian tail bound, we did is use Lyapunov drift analysis. Yeah. So that's why I'll get there. Yeah. Okay.
Nice.
But it's very interesting. I definitely look forward to see how the heavy tail actually can help in the reinforcement learning setting.
Sure. Yeah. Thank you very much for nice questions.
Yeah. Thanks a lot for the talk. So Vijay, I'll stop sharing. And,
sure. No, I will share now. So I guess share content, the screen. That's fine. All right, so mine is going to be a little, from start. So Mert, again, thank you for a good, excellent talk.
Thanks very much for listening. Can you hear me? Okay.
Well, I'm here, but for some reason it's not working. Okay, 1 second.
Yeah, sometimes when I don't go to full screen, it works better for me for some reason.
Yeah, so let me cancel. No, it's fine. Let me get out of this. Okay, this is fine. This is okay. We can go with it. It's not any great stuff in here. So the first thing this is actually related to the point that you were making about your estimates for the heavy tail distribution parameters. These tail index estimators are quite tricky.
Yes.
And actually, it's very hard to distinguish between many processes. Actually, these estimators are pretty bad. In fact, there is a work of a friend of mine, with a listing here.
Right.
Basically, they say that even if, so this is for long-range dependent processes, which tend to have these heavy tails as well. And there can be lots of ambiguities in estimating these critical exponents. And there can be it need not be the, so you have some theory to back up for the linear regression, but it's even for the deep neural networks, it may not be that easy, straightforward, and you may get some false.
Yes.
So one thing I wanted to ask was basically how
do we estimate?
How accurate are those estimates in some sense?
Right. So this is an excellent question. So there are different type of settings, results. So one is like, for instance, you see the values of a stochastic process and you go and back and try to fit some index, right? So that is the hardness that you are talking about, right?
Yeah.
So yes, from the sample paths, I agree it's hard, right? So what we are doing is we are doing something a bit simpler, right? We go, let's say I am at this point here, I compute 1 million stochastic batches, right? And I have a very accurate estimation of the, let's say, of the distribution, right? I am at a single point. At a single point, it is more about estimating the tail index at that particular point, right? Because I have fixed my distribution, at this point X, what is my gradient? But again, even for that, actually, these estimators are tricky. But theoretically, we can show that the alpha stable estimators are more accurate. Because let's say, if you don't know your class of distribution, it's a harder problem. So, but because when we average iterates, in the linear regression case, because we can show that it's going to be like an alpha stable distribution, we can make use of these more accurate estimators that are not generic, that could help. But this is an excellent point. So it is not that trivial to estimate these components. But again, like if you do something simple, like if you do something like, Shapiro-Wilkinson test on the gradients, that's not too hard to do. And if you do that, you still see non-normality. But you're right, these things are very hard to estimate. It's not easy. This is an excellent question, yeah.
All right, so my next question, this will start getting more speculative in some sense. Right. And so one was this connection to simulated annealing. Right. This is actually related, all of this is sort of in that sense. You mentioned Bruce's paper on optimal cooling schedule, right, and how height of the local optima.
Right.
So so if I may paraphrase what you said, basically the fact that you're using Levy processes, so you have jumps in the processes, and those jumps can allow you to escape these things. Is that a good summary in a sense?
Exactly. And because of these jumps, I can use less conservative step sizes. Like Bruce's paper shows that you need some sort of log type of cooling, right? So in the processes, we can get away with slower, we can get away with faster cooling, basically. So we have a theory for it, like how to arrange these cooling schedules. Exactly, it is like you are absolutely right about it. Yeah.
Hey, Mark,
so the other parts are more with respect to the mixing property. So you have multiple local minima. You're saying you're going to spend time in most of the process spends time. So basically, you're coming up with things like metastability, right? So basically, these are things with multiple equilibrium points.
Right.
But then you have more involved things there, because so the way that analysis works is basically first you have to get into some sort of, you get close to one equilibrium, then you can spend a lot of time in one equilibrium before you escape to the other one.
Exactly.
So you know how, I mean, what the time scale is, because a lot of your analysis seems to be on the stationary regime.
Right,
but
exactly.
The stationarity might be very, and that's sort of related to what I'm going to mention the next topic also. Seems a lot of this is related to the Friedland-Frenzel theory of
exactly
dynamical systems. But there, I mean, one point there is there's a difference actually between continuous time systems and discrete time systems.
You're right.
In continuous time systems, you would typically not get periodic type orbits, and you get more other behaviors. But in discrete time systems, you can get some periodic orbits, and
right.
So even knowing the equilibrium things may not be the right thing, because you may not even hit any of these local minima. You may be circling between.
Right, you're absolutely right. So we actually had a few papers on metastability. I couldn't talk about them today, but you are right. And I think this, so what's happening is that the mixing properties is different, as you mentioned, and we can characterize it. I think this may be related to the question that Lei also brought up. So the mixing is exponentially slow in dimension in Bruce's paper, right?
Yeah.
Here, we can show, it's actually known, we don't have to show, it is a polynomial in the dimension. It scales like 1 over d to the power of alpha. Alpha is your index.
So it's fast mixing in that sense, as they call it.
It's fast mixing, and that also depends a little bit on your width, because if the width is large, to be able to jump over it, you will need more time.
Okay.
But we understand metastability. Then the question is, can you prove something about the discrete process, because SGD is discrete?
Yeah.
The answer is yes. The way we do it is we look at, so in my PhD, I worked on numerical analysis. So we kind of use some numerical techniques. If the step size is very small enough, we can have bounds on it. Then we can argue that the metastability properties will be inherited. But those analyses, I think, are still not tight, because let's say we need step size less to be, let's say, less than 1, but it may be in practice, maybe you can use larger than 1. So we can do certain things, but as you mentioned, discrete systems are getting more tricky. But this is absolutely correct. So there is metastability phenomenon is related to what people call Cramer's law in physics. And the way to derive Cramer's law, you can derive it using Friedland-Wenzel type of theory as well. And there is that type of theory can also be done for Levy processes, and you could get what people call like this metastability results with this type of Friedland-Wenzel type of theory. So you are right, actually. This is exactly a good point. So
yeah. So my next question was more. More along the Levy processes thing. So there is a rich theory for Levy processes driven SDEs, and so there must be. So do you know if the analysis there? So normally the Friedland-Frenzel type analysis is more like large deviations. But here is it? I mean, so basically, is it more along moderate deviations, as in like nonlinear scaling, as opposed to the linear type scaling that happens?
So I'm not familiar with moderate type of deviation results in the Levy processes. But I'm aware of sometimes something like central limit type of scalings. So
so moderate deviations is between central limit, and so central limit is like square root n scalings, and you want large deviations typically, I mean, very loosely put, as like 1 over n scaling.
Exactly. So these two things exist, but the guy in the middle, it doesn't exist. I mean, at least I couldn't find it after like 2 years.
So if you look at so there's a way to define large deviations in a. So basically, you will say you take the log of the thing divided by log of the distribution divided by the sequence, right? The scale at which you go to infinity. So that doesn't have to be n. It can be slower than n, and can be, and that is sort of going towards moderate deviations. It's a nonlinear scaling in some sense.
Well, it might exist. We should double check. But even if it exists, I believe it will be more in a pure math type of community. I don't think that like the sort of connections to this deep learning is explored. But
yeah, may not be. But I mean, maybe there is a direction there that can help establish some of these.
Right. Exactly. I think it would definitely help, because when you do large deviations, you just talk about very long-term behavior. Like you need to wait a bit to get it. And for instance, if you want to do inference with stochastic gradient, then you need CLT type of regime. And probably the middle regime that you mentioned should be useful as well, like to get the fine-tuned sort of behavior. Yeah, I think, but it's not a very common thing to look at in math, I would say. But definitely it will be very interesting.
But if Levy processes, I mean, in the financial math side, they may look at it because they get sometimes look at Levy.
Right.
So the last sort of topic in a way is, so in some sense, you're arguing for Levy process-based noise, but it's not clear that your noise is independent increments. So you're saying maybe it's martingale difference, yeah, but it's zero mean, but it may not be independent increments. So do you think something like a fractional Brownian motion based thing might be a better way to look at it? That was one sort of direction. And the other, and that tends to have, I mean, I guess those things usually come up for long range dependent processes. Maybe yours is not long range dependent, so maybe it's not a right thing to look at there. The other thing I was trying to understand in some sense, I think this is also connected to Lei's work, was so you have this in linear regression, you have this multiplicative form, random matrix thing. But usually when you have this type of multiplication things, you tend to come up with log normal distributions. But is it the fact that you have also a linear term that is causing this? You have two forms of noise which couple together and become.
You have this multiplicative plus additive, like it's the combination of it.
Is that combination causing the heavy tail behavior? Or, I mean,
exactly.
Not log normal type. So log normal is heavy tail, but it's all moments exist. It's a
right. So I think
the border.
That's correct. So if you don't have the multiplicative part, then you don't have heavy tails. If you're like if you think about linear evolution plus noise, you stay as a Gaussian process and it doesn't happen. So this multiplicative part is important, but it depends on which limit you take. So if you take the limit, you have the Ornstein-Uhlenbeck, right, process. So if you take the limit, you can have the noise part depending on x, and in continuous time you could have a log normal as a limiting distribution in continuous time. But somehow in discrete time you don't get it. So I think this is the difference between discretization versus the continuous time. I mean, somehow your error is finite in time t, right? But your discretization error blows up with horizon. So that's why I think what happens is that there's a difference of behavior in discrete time versus the continuous time process. Maybe the process is good for finite time, but in infinite time, I think you see a deviation from the behavior. But you're absolutely right. If you look at, let's say, this sort of refined Ornstein-Uhlenbeck type of thing, where you have a noise that depends on your state, then you will see a log normal behavior. It's an excellent question. So I think, this, so we try to do like more general noise models. So right now we try to handle this martingale difference and so on. We can also handle it. So we now have a recent version where we can do like this martingale increments. But maybe looking at this more general processes, maybe it can be a better model for things, because at the end of the game, like the continuous time things are easier to deal with. So I think, definitely it's open. Like, how do you better model in continuous time is an open thing. I think like what we do is just an approximation, right? So maybe you do higher order, second order, third order, and maybe better. So definitely, I think it will be interesting.
So thanks so much for an excellent talk and for answering all the questions. Or at least I'll clap for you. So it's not anything else.
Thanks very much for the invitation and really nice questions. And
hey, Mert, if I may, can I ask a quick question?
Sure.
So can you explain why if the width of a local minima is larger, it's better for generalization? Is there any theory behind that?
So, I mean, essentially, so if you talk to very empirical people, they are like, oh, of course, this is like empirically, I have written 20 papers on it.
Right.
But the paper I cited, I will send you the slides, Hochreiter, Schmidt-Huber, actually, you can think of a Bayesian type of analysis where they have a Bayesian type of framework where they argue that this is better, but it's a little bit like it's not a superbly sound theory.
Okay.
But if you can come up with one, I think it would be really interesting. I mean, but this is something you see in the literature as an empirical result.
Okay.
Thanks very much. So
yeah, thank you.
All right, thank you. And yes,
talk to you later. Talk to you both later.
Bye.
Thanks.